We're going to talk about tribo-corrosions and problems related to that. Tribology is a word coming from the Greek word tribo. It's the study of interaction of two solid surfaces in relative motion. It's the branch of science and technology dealing with the principles of friction, wear, and lubrication. Here you can see the types of wear. These adhesive, abrasive, fatigue, and corrosive wear. And there is high rate of wear when a mechanical type of wear occurs in combination with a corrosive wear. So what is the corrosion? Is a chemical or electrochemical reaction between material, usually a metal or alloy, and its environment that produces deterioration of the material and its properties. Here you see the types of corrosion. It's pitting, crevice, and galvanic, and fretting corrosion. Fretting corrosion is the result of a small amplitude oscillations between contacting surfaces. Tribo-corrosion now, it is a combination, it's the combined action of wear and corrosion. And there is a synergistic interaction of wear and corrosion phenomena on surfaces subjected to the relative contact movement in biological environments. So it is important to be in biological environments, and these phenomena get worse. There is metal-related problems, not only metal on metal, but it's metal-related, and they create irreversible material degradation progress. And here is the mechanism of corrosion. It's a little bit complicated, but simple. It is cyclic loading on the hip joint, and there is head micromotion on stem taper and cyclic fretting motion. That it's creating repeated disruption of the metal's surface oxide, which is a passive layer protecting the metals, and repeated reformation of the metal surface oxide. The oxygen in the fluid joint is used for formation of the surface oxide, and there are some ions available to, for the chloride ions available to combine with the hydrogen ions and to form hydrochloric acid. And this acid becomes in the fluid, in the taper, becomes more acidic, and oxygen concentration drops, fretting continues, and corrosion and crevice deteriorate. So what about the implants and the resistance to this phenomenon? Stainless steel is prone to corrosion, but the resistance of the cobalt chromium alloys to corrosion can be attributed to the formation of the passive film, the creative passive film, which is a thin oxide layer that forms spontaneously on the surface of the alloy. Titanium, it seems to possess excellent corrosion resistance and is credited to the protective titanium oxide surface layer, chemical microstructure, and phase composition. But if you have a local breakdown or disruption of this passive metallic film, can start corrosion. The corrosion accelerates wear, and the wear accelerates the corrosion. Where are the locations, the localization of this phenomena? Relative motion between the contact surfaces has a major effect on the corrosion, and usually it's the burning surfaces, the taper junction and stem cement interface. And any modular connection involving metal alloys will show some corrosion if in contact with the body fluids and exposed to micromotion. That means on every prosthesis we are using, we have these conditions. And this is the result, fretting wear due to micromotion to the femoral cone. And then we have the taper with similar damage. We have seen in the presentations a lot of such phenomena. So what's the factors influencing tronionosis? It's implant-related factors, surgeon-related factors, and patient-related factors. What about the implant-related factors? The head size, the head offset, the alloy combination, the tranion geometry and topography, and neck flexural rigidity. What about the head size? In theory, if we have bigger heads, we have increased torsion and increased bearing forces in the neck of the stem. And there are some studies with some confusing results. Larger heads had more corrosion on the study you see up there, but there is no difference in fretting. But in the other, with the bigger numbers, there is neither fretting nor corrosion were correlated with the head size. What about the head offset? That's clear. If we are using femoral heads with offset greater than 5, then are correlated with more corrosion at the head-neck junction. Alloy combination. It seems that the titanium alloy, we know that titanium alloy is less stiff, less resistant to fracture propagation, and less hard. That means more susceptible to fretting, but it has greater resistance to material dissolution, as I told already, and that means less susceptible to corrosion. But the thing is that many times you combine different implants or combination of different metals leads to bigger damage in the interface, so we need to be careful on that. Tranion geometry, you have different tranions, different geometries, even from the same company, they have different geometries. So there is different fretting and corrosion scores between the tapers, so we need to know the taper, we need to avoid a few things. What about the topography of the tranion, microgrooved and smooth? No difference in fretting or corrosion between smooth and microgroove tranions, but it seems that higher tranion thread heights are protective of taper damage. What about the surgeon-related factors? It comes to us. Cleaning the tranion is very important. If you have a clean tranion, you have less micromotion, less wear. If you have blood and fat on the interface, decreases the disassembling forces, and contaminated interface exhibited significant larger micromotion and, of course, corrosion. What about the impaction force? We need to impact with the taper strength linearly increases with assembling forces, and what is the sufficient force is impaction force should be at least 4 kilonewtons in order to have good strength. So increasing the strength of the taper connection reduces the magnitude of micromotion at the taper interface and may prevent the initiation of fretting and corrosion. So that's important. What about the patient-related factors? Length of implantation. The longer the implantation, the more corrosion and fretting due to the more cyclic loading. BMI, higher BMI increases load at the neck, head-neck junction, increasing the possibility for fretting and corrosion. And the immune response, the degree of the immune response reaction to the metal debris differs from patient to patient. What about the ceramics? We heard a lot about ceramics. It seems that is part of the solution of the problem. There is lower fretting and corrosion, and ceramic head tranions demonstrated a lower median fretting and corrosion score. There are many papers supporting that. The total material loss from the ceramic cohort showed reduction in the amount of metal releases compared to the cobalt chrome cohort. So by using a ceramic femoral head, cobalt and chromium fretting and corrosion from the modular head-neck junction may be mitigated but not eliminated. So keep in mind, not eliminated. So how big is the problem of tronionosis? There are the clinical effect and the true incidence of tribo-corrosion remains elusive. So if you see in the literature, it starts from 0.032% and goes up to 2%, and in the National Joint Registry in UK, they report 0.75% of revisions in non-metal-on-metal total hip arthroplasties, and the head taper corrosion regarding to that paper in the effort review, it is up to 3%. What's the outcome? We have seen many pictures like that, just collecting everything. And what is the solution? It seems today that, first of all, we need to avoid modular connections, if it is possible, metal on metal in some categories of patients. You heard all those things, and we need to diagnose earlier the patient. And of course, we need to think pink. Thank you very much for your attention.